everyone, I'm Zhecheng Hu. I'm currently a fourth-year graduate student from Tsinghua University, and I'm currently also a visiting student at the University of Hawaii. I study exoplanet science. I do their atmospheres and also their dynamics. And yeah, so today I'm going to provide a basic introduction to Matplotlib, which is a library that we use a lot to generate the scientific figures. So let's get started. At the very beginning, I want to introduce a little bit of what is Matplotlib. So Matplotlib is a Python plotting library that generally used to produce 2D plots, but also supports 3D plots and animation. And it's called Matplotlib because it uses an API style similar to MATLAB. So that's why there's a mat in it. Um, and actually, most of the astronomy papers today are using Matplotlib, or it's maybe its neighbor libraries for plotting figures. And I want to introduce that we have a gallery on their website, which is a good place to find examples and inspirations. And now, if you have not installed Matplotlib, please run this very simple command in your terminal to install it. Just pip install Matplotlib. And here is one real example from my own from my own paper that are created using Matplotlib. It can show color bars and images and those points and lines, different styles and some text. Okay, so now let's get started. From the very basic point, I want to introduce how to generate the very first plot use single command, single line. Okay, so throughout this lecture, I will always have some kinds of code on the left-hand side, and the code will actually generate a plot on the right-hand side, exactly with this with the code on the left. And these two lines are import lines that defines the alias of NumPy library and the alias of Matplotlib pyplot module. And this line defines the random seed. So basically, this will not appear again, but they are always valid. And here is basically how we define the x and y data, and they will also appear in different form in the later slides. And here is the very simple command, the one single line that we use to generate the plot on the right, which is just plt.plot x and y. And the second step after we finish the plot is that we want to save the figure. There is a plt.save figure. I have commented it out because I do not want to save it again. So there are two types of save you can do. One is in the PNG format, another is in the PDF format. So in PNG format, you can specify the resolution. Typically 300 is enough for publication. And personally, I like a PDF format more because it's vectorized and we do not need to care about the resolution. And please remember to save the figure before you call this plt.show, because after you call show and you click when you close it, you basically lose it. And this line is also necessary if you use it to display the figure if you're running a .py file. However, if you just copy this kinds of command into a Jupyter notebook, then this line is not necessary, because nowadays I believe Jupyter notebook, they just do not require this line to show the figure. Okay, but the previous step just show this very simple plot, but they're actually not very pretty. So now I would like to introduce step by step how we add on more things in the plot. So basically, for pyplot, for plt.plot function, it plots some lines. For each line, we can specify 3 style components for them, which is the color, the line style, and the marker fit. So basically, these are just some strings that are called format strings, which defines the color, the line style, and the marker. And actually, people can combine these kinds of 3 things together. For example, GO dash means green and circle and solid line. And yeah, colors also accept other formats. You can see this cheat sheet for more options. And here is a demonstration. Yeah, this 4 lines and these 4 lines, they're equivalent. So you can choose either one. And basically, GO dash corresponds to this line. It's a green solid line with points on it. And RX means red cross, and like here. And this star basically, yeah, means it's star. And white is blue because that's the default color for Matplotlib.pyplot module. If you have not specified any color, it follows a built-in sequence, which is blue, orange, something, something, yeah, in it. So that's why it is blue. And B dash dot is this dash dotted line here, which has blue color. Okay, and here are some more, if you want more control in more detail, you can have some of these kinds of keyword arguments. It's like you can control the color, the line style, the marker again, but they're specified with the keyword arguments. And you can also control the marker in more detail and also the lines in more detail, but I do not specify them here. You can check the documentary. Basically, marker size, color can be changed. Yeah. And here are some abbreviations if you feel too tired to basically write them in a whole. Okay. And you may have found that in the last slides, there is a very important thing is missing is the X and Y axis label. They are very important when we are making any scientific plots. We always need to specify the X and Y axis in scientific plots. And here is how we do it. We basically use plt.x label and plt.y label to add X and Y axis labels. And you can also specify the axis range, the x-axis range and y-axis range. You sometimes create a zoom-in plot by using these 2 kinds of limit. Okay. And if you read some scientific papers, there are also some other common features that you can specify. The first is that people sometimes like to have 2 kinds of conventions in scientific plots for the axis ticks. The first is that people sometimes want both the major ticks and the minor ticks so that they can have a more detailed notice of the axis here. And also people want to point the tick axis inward rather than outwards, which is another convention. And if you are plotting multiple things in one plot, you also want this axis to demonstrate, to tell your readers what are these lines corresponds to. So these can be done with this. For example, this labels controls where the legend is, what's the label of this sign. And to present the label, you can use plt.legend here. And this minor tick sound creates this minor ticks, and basically this direction equals to in makes the pointing towards inside the axis rather than outwards. Okay, and we can also have some annotations. For example, you can use the annotation, which is the arrow with the text, use plt.annotate function and plt.text function. If you sometimes found the legend, you have found the label of some object is you do not want the label to be on some of the corner. You want it to put it more freely, then you can just put it by your plots. Like here, it says sin x function, which is basically this function. And peak basically starts at the text position and ends at the arrowhead position, like it's shown here. Okay. And since this is an international course, I believe there are also some kinds of needs to display your own language, which is not default for Matplotlib, but nowadays we can do it very easily. So Matplotlib supports Unicode, but correct rendering depends on 2 layers. Basically, it says that you need to contain such character in your font. If your character does not contain this font, if your font does not contain the character, then yeah, you cannot do it. Some text shaping, but now we do not care about this actually, because Matplotlib has already handled this for us. So nowadays, it's very simple. You just define this in the beginning of your script. For example, you add some fallback font, like the CJK font for Chinese characters, an Arabic font for the Arabic characters, and this and that. And you can have some guidance for this, but basically, this is all you need. You define some fallback fonts, and yeah, everything is done. And here is the showcase to write hello in several different languages. And yeah, just to demonstrate this is okay. Okay, so the above, I have introduced some very basic functions of Matplotlib, but this time I think it is more important to introduce the idea behind Matplotlib. And then why is it important? Because once you learn the idea, you know how to describe something you want to modify. And then you speak the same language with your AI agent so that you can ask your AI agent to create a plot or modify a plot as long as you speak the same language in Matplotlib. So that's why I need to emphasize this. So now I want to introduce this kinds of concept of Matplotlib. So what makes up a plot? They're basically a plot can be considered as a three-layer concept. The first layer is a very basic layer. It's called a figure. The figure is basically the entire canvas. And yeah, it contains some kinds of the second layer. The second layer is this axis. The axis are these small sub panels that you're typically seeing in scientific plots. And yeah, inside this axis, you can have some objects of your of the things you have plotted. For example, you can have a line object, as is shown here, which is basically the line you have plotted. And one important difference is that previously we always use plt.plot, which also plots in an axis, but is always point to the current axis. But if you have multiple axes, this is can be very tricky because you do not know which axis is the current axis. However, if we use this kinds of ax.plot, we can explicitly know that okay, this is the axis that I want to plot it. Okay, so now let's see some examples. This is a very simple example that creates a 2x2 grid, uses this plt.subplot function. It's very simple. It's plt.subplot. It's how many rows you want, how many columns you want, and which index you want for this single axis object. So here I just iterate from 1 to 4, and to basically show you that the sequence of the index of the plot is basically from left to right, from top to bottom. So 1, 2, 3, 4 is the axis indexes. And here is the more realistic kinds of example that we define two axes, use a different kinds of method, which is figure.subplot. You can have two rows, one column. This is index number 1. An index is from top to bottom. So index number 1 is the upper panel. And index number 2 is the lower panel, which is this one. So you can use subplot to make this. But my personal favorite is this kind of method. It's called plt.subplots. This is the shorter form, and it allows you to create figures and axes all in once. So again, their languages is always very similar, 2 rows, 1 column, and we do not specify the axis indexes this time because it creates all the axes at once. The figure size defines how large the figure you want, and the aspect ratio of the figure. But yeah, that's not very important here. So basically, this is a figure object. and this is a two-axis object. Axis 1 and axis 2. So axis 1, again, it corresponds to index 1. You can name it to other things. For example, axis upper is named to axis lower. But remember, axis 1 corresponds to the first index, which is the upper panel as it's shown here. Okay, great. So one last thing is here the concept is, what does the figure do? The figure basically controls the layout of the between panels, or the layout of the axis. So after you have finished plotting, you have added your labels and titles, you can do kinds of adjustment. So there are two types of adjustment. First is the title layout. It calculates the space needed automatically and basically, do it automatically. The second is this kind of subplots.adjust. You can adjust the margin between those panels from the top and right and bottom and left edge of the figure. And you can also adjust the space between each column and each row using W space and H space. Okay, cool. An axis is actually very flexible. For example, plt.axis gives you a direct method to define how an axis object looks like. So for here, we can define an axis object is basically an inset axis. It provides a zoom in plot of here. So you can define it left, bottom, width, and head for this type of inset, and in the coordinate of the figure coordinates. And yeah, you can display, basically have overlap, overlap, subplot, or overlap axis that is useful and is very handy if you want to create some inset or zoom in plot. So this is the one recipe that covers most of the figures. So, okay, the default workflow is that I personally like start with plt.subplots and plots through different axes, and then add labels, and then finish and adjust the layout. And another tip is that I suggest, or I recommend you to keep your visual style constant, not among your different figures and even among your different projects. And because this saves you tons of time. And for example, you can get started from this GitHub repository, which some scientific plots here. Okay, and that is pretty much a very basic concept you need to know about. And from now on, I will be a little bit quicker and just to showcase some common plot types of different plots that gives you a concept of what's the capability of Matplotlib. So here is the scatter plot. You can basically have some scatters without lines. And here are some points with arrow bars, which is very commonly used in astronomy because we always need to quantify what is the uncertainty of a certain measurement. And this is called science, right? So basically I fix some data here and create this arrow bar. You can also do this. And another thing which is the uncertainty corresponds to is the uncertainty of the model. We always do some kinds of, we need to fit a model of something. And here is how we do to demonstrate the uncertainty of a model. So you can use fill between to specify some kinds of range that fill some color inside this range, or transparent color. So basically this is the model, and you can specify that this is the range. If you are fitting a model to this, or if your model comes with some kinds of uncertainties, you can use this very handy function to basically show what is the uncertainty looks like. And the histogram, which is handy when you want to show some kinds of distribution for certain plots, and pie charts, which is not very common in astronomy, but it's not bad to remember this, or not bad to know this at least. Okay, those are just one-dimensional plots. Matplotlib can also plot some two-dimensional plots. So for example, this is the image show function, which allows you to display a matrix as an image. It's a matrix, but actually I use it a lot to display astronomical images, because astronomical images is basically, they're just a matrix, right? So you can actually display them as well. And yeah, these are some, and these kinds of image show can also be used to demonstrate some kinds of model you want to, some kinds of model. You can use this mesh grid function of NumPy to create a grid of X and Y. And you basically can calculate them, calculate the value of X and Y point to point, because that's the convention of basically NumPy. And you can use image show to do this. And yeah, voila, here you go. This is you can visualize your model in this way. And some kinds of contour, you can use this to basically demonstrate, for example, the uncertainty and the correlation of two variables in your model fitting. Yeah, for example, this is your, let's say this is your kinds of uh yeah, kinds of slope of a line, and this is the y-axis position of a certain point on the line. So with these two things, you can specify a line. And yeah, if you do some model fitting, this is could be the uncertainties. And it could be some other things, for example, the gravitational potential of something, or yeah, some potentials. So this is contour F, which is basically field contours. They're just field and pretty much like the contour. Okay, and Matplotlib is also able to do some three-dimensional plots and animations. Here, basically, it's just a showcase, three-dimensional plots of some scatter points. Yeah, but please, yeah, know that I currently cheat here. As you can see, there is a video object. But if you run the above code and you do some kinds of plt.show in a Python file, you can also see the same kinds of figure, and you can also drag it actually. Okay, and another thing is that you can have some three-dimensional surface and projected contours. This is the plot surface function. You can do it to, for example, if you want to demonstrate your gravitational potential, how does that looks like? You can do something like this. Okay, and last is the animation. So basically, yeah, the animation looks like here. I converted it into HTML, so I can play it here. But yeah, you can also save it into some kinds of MP4. You can look up them online. I do not have time to cover them all, but basically just to showcase that animations can also be created with Matplotlib. Okay, good. Okay, panel. So now we all know that now it's 2026 rather than maybe 2010 or something. So nowadays, technology has evolved, especially the AI technologies. So you may find that it's tedious to remember those all kinds of commands, the functions, the keyword arguments within your brain, because previous days, what I usually do is that when I plot, I rely on the cheat sheet and the documentation of Matplotlib a lot. But nowadays, with AI agent, we do not need to remember all of this. All you need to know is that what is the capability of Matplotlib, and what is the language of Matplotlib, the three-layer concept of it. Then you speak the same language with your AI agent, because AI agent already know this, and you can ask your agent to do this. Okay, so this is basically the typical workflow of how to make plots with AI agent. So we should work within a project folder, not in web chat interface, so AI agent can know what your data is. And we want to write a specific prompt. I will not go through this all in once, because I will have an example later so we can know. And after that, the most important thing is that you need to always check the figure generated by your agent. If a major changes or some multiple modifications are needed, you can ask the AI agent to modify the script rather than do it yourself. However, if the changes is only one or two minor changes, for example, you just need to modify kinds of your font size or the line colors, then you just need to do it yourself. It's typically more efficient. So this is an example that I want to show that we can plot the HR diagram or the Hertzsprung-Russell diagram using Gaia data. The Gaia satellite has measured the brightness of and some other properties, especially the distance of over 1 billion sources. And the HR diagram basically compares the stellar color with its absolute magnitude or its luminosity. So our goal is to use the Gaia DR3 source to plot an HR diagram. Um, so step number one is that we want to download the clean Gaia DR3 sample. I have already prepared a link here that you can download them directly. And yeah, here is some selection, some explanations for selecting this sample, which is not very important now, but yeah, it's useful to, if you are interested, you can dig into this later. So step number two is that we want to give the agent a reproducible prompt. So basically, let's go through this now. So first thing, I want to specify which data I want to use and what plot I want to have. And next, I specify how to read the CSV file. Do not use NumPy, use pandas. This is more convenient. And then, actually, this is not necessary because AI knows what HR diagram is. But if you're come up with your own kinds of diagram, you need to tell what's the x-axis and what's the y-axis is. And also here I specify what's the model is, how to compute the absolute magnitude. AI also knows this, but yeah, just as an example, because sometimes you will have your own models, which then becomes necessary to specify them. Okay, and invert the magnitude axis because this is a convention in astronomy. The smaller magnitude means brighter flux. So basically, magnitude axis should always be inverted. And I want the points to be semi-transparent. These are style requirements. I also wanted to plot the position of the sun with a red star marker and save the scripts to these kinds of things. So this is a relatively complete prompt. Specifies the input, what's the calculation, what's the model is, what's the plot design, and where should be the output is. So basically, this is a very simple case. You can come up with your own, but this prompt basically gives a very simple script with 19 rows and generates the HR diagram on the right. You can say, okay, here is the white dwarf, and here is the main sequence, which is relatively complete. I'm happy about this. I do not want to modify it later. But if you want to modify it, you can basically complete the loop. You just ask the agent to modify the plot again. Okay, this is pretty much it. So I want to emphasize that one thing here is some recipe. I will not go through them because I have already go through them for a very long time. One thing I want you to remember is that nowadays concept is more important than to remember every detail of the functions and the methods and the keyword arguments. So you understand the concept, the 3-layer, how does Matplotlib generates the plots, and you understand this concept, so you speak the same language with AI agent, and you can basically tell agent which part to modify in a more precise way. And you build the plot with your agent within this recipe, and you basically check it and then you modify it. That's pretty much what we need nowadays. Okay, thank you. I believe that's all.
Right. Any questions? Feel free to unmute yourself or just type in the chat. All right. If there's no questions, are we using Seaborn as well? Yes, Seaborn is another useful package in Python. some people argue it's more convenient in Matplotlib. So if you'd like to try Seaborn, feel free. All right, moving on to the second part of today's session. Just NASA Exoplanet Archive. Let me start the video.
Hello, my name is Mutian Wang. I'm a graduate student at Nanjing University, and I study exoplanet. So today I'm going to introduce you to the NASA Exoplanet Archive. This is a really useful public database for exoplanets where you can access the information of either a specific planet or construct a sample of planets belonging to a population. So this is the front page of Exoplanet Archive. And on the top, you will see 4 boxes showing the current statistics of the confirmed planets. The first one, it shows by now there are over 6,300 of confirmed planets. And among this, the TESS, which is a space telescope that is discovering the planets through transit photometry, it has contributed about 900 of confirmed planets. And also it has delivered thousands of planet candidates that await some additional follow-up observations to confirm their genuine exoplanet status. So on below, there's a search window if you want to look for a specific planet for its information. So I will show you how to do this. For example, if we want to look at the very first exoplanet that discovered, which is called 51 Peg B, you type the name in and you click the search, and a new window will pop out. And this will be the overview page for this planetary system. So this is the page. On the top, it gives you the architectural overview about the system. This planet orbits a sun-like star that is 20% larger than our sun and slightly hotter than our sun as well. And the system contains only one exoplanet, 51 Peg B. And down below, there is a brief listing of the basic information about these planets. This says it has an orbital period about 4.23 days. Its mass is about 200 of Earth's masses, and it's discovered by the radial velocity technique in 1995. And it is firstly announced in this reference. So you can click this link and it will direct you to the ADS database, to the literature that announced the presence of this planet, where you can explore on your own. Okay, backing the page. There are 2 entries here. One is for the parameters for the whole star and parameters for the planets. So if you click in, there's a plethora of parameters that are related to this star, including its coordinates on the sky, how bright it is. So its V band magnitude is about 5.4. So it's a naked eye star. Then this table lists out a few extra parameters for the star. For example, the radius, the mass, the temperature, and the luminosity of the star. And over the years, there has been a lot of literature that is studying these particular systems and coming out their very own parameters. And the database will list out them comprehensively. and you can compare them between different literatures. And whenever necessary, you can just click the link here and see the literature that is studying this system. And similarly, for the planetary parameters, there are even more comprehensive parameters listings for these planets, including the orbital period, semi-major axis, meaning how far it is from the host star, its planet mass, orbital eccentricity. It describes how elliptical is the orbit, inclination, and so on and so forth. And finally, there is a reference list that is covering about this planet in general. So now you know how to look for specific planets in the archive. Okay, let's now go back to the front page and explore other functions. So on the right here, this is a news window. It just presents a weekly updates to the database. So the database is still in the is actively maintained every week. There will be new entries of newly discovered exoplanets, and they will write a newsletter to cover about this. And also there's some pre-generated plot here to show the distribution of the current exoplanets. For example, this figure shows the planet's orbital period versus its mass, and it's also labeled by their discovery method here. And there are a few other examples for the pre-generated plot you can explore on your own. I will not go into that. And on the left, this is the database for grouped by the mission. So here it is showing the data that is accessed by the James Webb Telescope. I think in the next week's session, you will learn about exoplanet atmosphere. It is a very exciting field that is advanced by the James Webb Telescope for now. And also there are data from TESS. I just covered about that. It is a space telescope looking for transiting planets, and also Kepler and K2. Kepler is a predecessor to TESS. It is also a space telescope that is discovering transiting planets. But it actually has some difference in the search strategy and design in the telescope. And this will be the focus of the later notebook tutorial. So let's wait for that. On the very bottom, there are a lot of shortcuts to multiple functions and features that is on this website, which is very useful for the exoplanet research. So, but I will not go into this today, but if you can play with them on your own. So I just showed how to access the information of the specific planets. Now let me show you how to access the database for all the exoplanets. So hover your cursor here on the data, then you will see there is a numerous catalogs on this website. And I will be focusing on this planetary system composite data. It contains all the exoplanets for their parameters gathered from different sources. So it's a very comprehensive catalog. So click in, you will see a very large table here. On the bottom, it says it has 6,300 of entries here. That's the number of confirmed planets we just saw. Also, there are multiple columns in this database. It has shown a lot of information about each planet. For example, what is the discovery method of each planet? What year is it discovered? The radius, of these planets in Earth unit and Jupiter radii, and also their coordinate, sky coordinate, their distance to our solar system, and so many others. And for this white boxes here, this is the place you can apply several criteria to filter out a specific subset of exoplanets you are interested in. So to give an example, if I'm only interested in transiting planets, so I just type transit here, then it will just give you a shortened list of exoplanets that's discovered by the transit method alone. Also, you can apply several criteria at the same time. For example, if I want to see the planets that are discovered by the transit and has an orbital, the planet radius is smaller than 1 Earth radii, then I will just type smaller than 1 here, then it will give you some exoplanet information that is very small here. Okay, so also you can just click in the planet name here and we direct you to the overview page for this specific planet system. And although there has a lot of columns and properties on this table already, but there is still some missing information here. For example, if I want to know how old is this system or the stellar age, it is not shown here. So one way to look for the unshown columns is to use this select columns icon. Then it will show you some extra displayable properties of these exoplanets. So for the stellar age, we'll look for the stellar data. Then we can find stellar age is here, but it's not clicked. So it's not checked, so it's not displayed. So check this, then click update. Then the whole table will be updated. Then you will see the stellar age is listed here. Okay, finally, I will let you know how to download this entire table here. So let's remove the criteria we exerted before and refresh this table. Okay, so the table is back as the original one. Then we click, if you want to download the table, just click this, then select the download data product you should expect in this format of CSV. It is the easiest format to be digested by Python code. Then you click download the currently checked columns. All the display columns will be downloaded. Then you just click the download table and a download will start shortly launched. Okay, so let's proceed to the tutorial session. So as I have told you, this tutorial will give you, in this tutorial, we will be dividing the exoplanets into the planets that is discovered by the Kepler and TESS. And we will see some difference in the planet yield between these two missions. So by the end of this notebook, you will learn how to load the exoplanet archive table into the Python. And you will also know how to select the planets that is discovered by the Kepler and TESS respectively. Then you will make a period radius diagram for these two subsets of planets. And you will see some difference in these two plots. And you will learn why is this different? Why Kepler and TESS so different in their planet yield? And for the last part, your assignment, you will plot a radius distribution to the planets discovered by Kepler and TESS and identify a feature called the radius valley. Okay, so let's get started. So for Kepler and TESS, both of these missions use the transit method. They just look for tiny dips in the star's brightness when the planet passes in front of it. But their survey strategies are very different. Kepler actually just stare at one particular patch of the sky for years. This is for the purposes of enhancing its capability to discover very small radius planets. Whereas the TESS is more in the survey mode. So it actually just survey almost the entire sky and just focuses on finding exoplanets on the nearby bright stars. Okay, so for the first session, we will import some relevant packages in Python, including the NumPy, Pandas, and Matplotlib. I believe you just learned from the last session how to use the Matplotlib here. And also the magical code line Matplotlib inline just guarantees a plot will immediately show up after you execute the code. Then you do some setup to the display of the figure to make sure you look better. Okay, for the second part, we'll just load the Exoplanet archive database into the Python. So usually the database downloaded from the Exoplanet archive will have a prefix, something like the PS compars. So this stands for the Planet System Composite Parameters. So we will look for some file names that starts with these words in the data framework. Okay, so to make sure you will find the data, and we will load the data by the pandas data frame. And to make sure we are loading it right, we'll print out the length of the table and how many columns are there in the table. And finally show the first 10 entries of the table. Okay, so it's successful. So we are accessing this file under the folder of data, and it contains 6,300 of exoplanets. So it's this is the number of confirmed planets we just see on the web page. And there are 84 columns or 84 properties related to each entries. And this is the overview of the loaded database. So this is a very, very comprehensive parameters for each planet. But in today's notebook session, we will just use these 6 columns we are most interested in. They are the name of the planet, the name of the discovery facility or mission, and also the planet orbital period, planet radius in Earth radii, and the planet mass in Earth masses, and finally the mass provenance that shows what's the source of the mass measurements listed in the table. So we will group these columns in the list. Here, just type them in, then we'll just see the selected subset of the table. Okay, so there are only 6 entries, or 6 columns for each entry in this table now. Okay, so going ahead, now we will be selecting the planets that discovered by the Kepler and TESS and creating 2 subsets of tables. This will be done by selecting their discovery facility equals to Kepler or TESS. Okay, so this is the full name of the TESS telescope, which is this Transiting Exoplanet Survey satellite here. Okay, so first of all, we will clean up our table to make sure there's no empty values in the orbital period and planet radius for the entries. So we'll apply this line. Then we will select the Kepler finding planets, ensuring the discovery facility is Kepler here. Then we'll do the similar things to select the planets that is discovered by the TESS. Then finally, we'll print out the number of entries in each subset here. Okay, so it looks like Kepler has discovered planets about 2,700 here, and TESS yield is only 1/3 of that. Because it's serving a nearby bright star, so the TESS yield is a little bit limited here. Okay, finally, we can start to making our first plot, the period and radius diagram. So to do this, we'll just to make sure our figure axis is in the right range of the displayed data range. So we are making sure the range for the x-axis is correspond to the minimum and maximum value of the orbital parameter, and the same for the radius in the y-axis. Then we'll plot the orbital parameter and radius. Also, we will be plotting our own Earth to compare with the exoplanets. Then here we go. Okay, so these two figures are the Kepler and TESS finding planets on the period and radius diagram. And this is our own Earth, the green star here. So I think one thing that is very clear here is that most of the exoplanet system, they are very short period, in the sense that they are shorter in period in our own Earth, which has a period about 365 days. And also for the one Earth radii, this is our Earth, and our Neptune is has a radius about 4 Earth radii. So you will see our own solar system has terrestrial planets like the Earth and ice giant planets like the Neptune, and the gaseous giant planets like the Jupiter or Saturn is on the 10 Earth radii here. But actually from these two plots, you will see there's a very crowded region between 1 and 4 Earth radii. So these are the planets that are not present in our own solar system, but they appears to be more common in the general galaxy context. This is the type of planets we call super Earths and self-Neptunes here. So this is the region that is really crowded, but there are also some places that is sparse. So you might see in the vicinity of the Earth, it's very sparse. And in the region that is on the orbital period of a few days, and in the size intermediate between the Earth and the Jupiter, there is a deficit of planets here. This is what we call the hot Neptune desert. And the reason why this region is sparse is that these types of planets, the hot Neptunes, they are genuinely rare. Whereas for the Earth, it is not so clear. Most of the reason why this region is not that populated is that both the Kepler and TESS does not have reached the capability or enough precision to find Earth-like planets here. And also, you probably will notice that the TESS mission has less Earth-sized planets than the Kepler finding planets here. And this is because TESS is not looking for very small planets in the all-sky survey. So Kepler is actually staring at a particular field of stars to enhance the precision and with a goal to find smaller planets. Whereas TESS it's not staring, it's doing a survey mode. So its ability to find small planets is not as strong as the Kepler mission. So this is why these two surveys seemingly yields different populations of planets in their yield. Okay, so that's for the online tutorial. I believe this notebook will be available on GitHub shortly after this. And for the take-home assignment, you will be plotting the radius distribution for the Kepler and TESS finding planets and try to identify a feature that is called the radius valley, which is a dip in the number of planets that is around roughly 1.5 to Earth's radii. And this will just mark a transition between the smaller Earths, super Earths, and the larger sub-Neptunes with thicker atmospheres. So I have you will be plotting these distributions with the two subsets we constructed here. And you can tell, maybe you can tell a difference in the radius valley feature between these two missions. Okay, I think that's all for today's introduction, and thanks for listening.